What if I told you that a machine capable of powering an entire city is quietly boiling water, without flames, without smoke, and without burning anything at all? This machine exists, and it's called a nuclear reactor. At first glance, nuclear reactors seem complex and intimidating, but when you strip away the myths, a reactor is not an explosive device. It's a carefully engineered heat source. Its job is simple: produce heat in a controlled way, then use that heat to generate electricity. Everything begins inside the reactor core. This is where fuel rods are arranged in a precise geometric pattern. Inside those rods are uranium pellets, small, solid cylinders that store enormous amounts of energy. Uranium atoms are naturally unstable. When a neutron hits one of these atoms, the atom splits. This process is called nuclear fission. Fission releases three things at once: heat, radiation, and additional neutrons. Those new neutrons move outward and strike other uranium atoms, causing them to split as well. This creates a chain reaction, but not the kind you might expect. Unlike a nuclear bomb, a reactor is designed to slow the reaction down. The goal is steady energy, not sudden release. This is where the moderator comes in. In most reactors, ordinary water plays this role. Neutrons released during fission are extremely fast, and fast neutrons are actually less effective at causing further fission. Water slows them down just enough to keep the reaction efficient and predictable. Without a moderator, the chain reaction would fade. With too little control, it would accelerate. Balance is everything. Control doesn't stop there. Between the fuel rods are control rods made from materials like boron that absorb neutrons. By inserting or withdrawing these rods, operators can fine-tune the reaction in real time. Insert them deeper and power decreases. Pull them out slightly and power increases. This allows reactors to respond smoothly to changes in electricity demand. As fission continues, the reactor core heats up. This heat is transferred to water circulating through the system. In many reactor designs, this water is kept under extreme pressure so it does not boil. Instead, it carries heat to a secondary loop where steam is produced. That steam is what drives the turbine, a massive rotating structure connected to a generator. As the turbine spins, the generator converts mechanical motion into electrical energy. From this point on, nuclear electricity looks identical to electricity from coal, gas, or wind. The power grid doesn't care where electrons come from, only that they arrive. One of the most misunderstood aspects of nuclear reactors is radiation safety. The radioactive material is confined inside multiple protective barriers: fuel cladding, a steel pressure vessel, and a thick concrete containment structure. The steam that spins the turbine never touches radioactive fuel. It comes from a separate, clean water system. Reactors are also built with layers of automatic safety. If abnormal conditions are detected, control rods drop into the core instantly, stopping the chain reaction. This rapid shutdown is known as a scram. Even after shutdown, cooling systems continue removing residual heat to keep the reactor stable. Modern reactor designs go further. Many rely on passive safety, using gravity, natural water circulation, and physics itself, not computers or human input, to maintain safety during emergencies. So why use nuclear reactors at all? Because they deliver immense energy from very little fuel, operate continuously for years, and produce electricity without carbon emissions during operation. A nuclear reactor is not a mystery box or a ticking bomb. It is a machine built around precision, balance, and control. One that turns the energy locked inside atoms into something remarkably ordinary: electricity.